Hi friends, let's have a look at today's daily challenge problem. Problem 1593. Split a string into the max number of unique substrings. This is a good problem for demonstrating or practicing backtracking. So first we'll look at the problem statement and then we look at the coding. So in the coding part, we're going to present two formats of backtrackings. So these two formats are actually the same solution, but some people may prefer one form and some people may prefer another form. So with that said, let's now look at the problem statement. So here we are given a string. We want to return the maximum number of unique substrings that the given string can be split into. So we can split string S into any list of non-empty substrings. So here non-empty is important, where the concatenation of the substrings forms the original string. However, we must split the substrings such that all of them are unique. So here are three examples. So let's first look at example 3. So if you have A and A, there are two A's, you cannot split it into two A's, right? Because they're the same. So we can only return a list containing the original S itself, so the output is 1. So for the second example, if you put a split at the after index 0, you get A and BA, right? So you cannot place two, like one after A, one after B. So you will get A, B, A, but the two A's are the same. So this gives 2. So for the 2 can also be obtained from you put a split at after index 1, you get AB, then you get A, right? So for the first example, there are 5. The largest one is 5. It says that one way is like this. It also tells us it's not unique. Though the maximum length might be is unique, like demonstrated in example 2. So with that said, we are ready to look at the coding. So for the coding, we're going to use backtracking and bounding, right? So the backtracking basically is that we want to find all the possibilities, and then we're going to use bounding conditions to stop the backtracking procedure. So here another thing to notice is that we need all the substrings unique, right? So this is the condition. So you can draw the say decision trees so to demonstrate this. For example, I can use this A, B, A, right? So you can split from A, right, or split from AB or ABA. So if you use the last one, it's already done. So you are going to get so corresponding to a split length 1. But if you first do A, right, then you can do B next, and you can do BA, right? So if you do B, so you are going to get ABA. So this is not valid, right? So this is not right. If you do A and BA, so A and BA, you already get So let's see A, BA, and A, B, right? So let's write like this, BA. So this will not give you a valid split. This is a valid split of length 2, right? So then you can consider the second branch. So you have AB, right? Up to here, you can only get A. So this is okay. So this length is also 2. Another one is you have ABA. So length is 1. So among those, so the largest one is 2. So we're going to return 2 for this example. For the first example, it will take some time to analyze if you want to draw this discern or branchings. So you can try to draw those in a white paper to see what you get. So with that said, let's look at the coding. As for the coding, if you have practiced a number of backtrackings, you might notice that there are several patterns or there are several formats you can follow. So in the first format, so I'm going to do the following. So first I'm going to get the length of this string, So this is for convenience, right? Length of the string s, this for convenience, right? So now I'm going to get a result. So this result is to hold all possible splits. So this splits, each split corresponds to a list of strings, right? And then also I want to use a current split. So this is a list containing strings. So this is to be used to build each individual split. Then we are going to write a hyperfunction. So this is essentially recursive backtracking. So I'm going to use DFS, right? So then the input will be a starting index, right? So first, a bounding condition, right? So if idx equals n, so in other words, out of bounds, so you can write it as greater than or equal to n. So essentially it's the same effect. So it means that we have finished a split. Then what we are going to do is we are going to append a copy of the current split. Let's use a set, right? So because we want to make sure all the substrings are unique, so we can make a copy of those one. Because later in the process we are going to modify this variable, so we put a copy, right? So then we are going to return. So this is the bounding condition, and then we are going to do the main backtracking step. So we can, from the current index, we can try, for example, the current index itself, or we can try the next three, but all starting from the current index. So let's use a for loop. So for I in range, so idx up to n, right? So this range will end at n-1, right? So then what we are going to do is that we want to have a word which actually is a part of the string s, start from idx and ending at index I. So we are going to write I plus 1 here, right? Because this endpoint is not included. So this is the word we are going to add, but it's possible that this word is already in the current split set, right? So we want to eliminate that possibility. So basically we can use an if condition. If word not in current split. So in this case, we can continue our search. So we're going to do DFS. Because we have used up to I, then we are going to start from I plus 1. And so here we forgot something, because we want to use this piece. So we're going to do current split, so add, because we are using set, so we're going to add this word. And then we are going to use the current state of the current split set, right? That also explains why we append a copy to this result, right? So then what we are going to do after this, so we are going to traverse back to the previous state. So it corresponds to remove the word. So this is our main backtracking function. So what we want to do is actually call this function, right? So this function will construct each individual split. And then if we have a valid split, we're going to add that result to the result variable or result list. Then this is the effect of just calling this DFS, starting from index 0. Then what we want to do is to return the largest length of the sets in the result list. So this is rather straightforward now. Return, so the max, so we can compute the length of a set, right? Atom. For atom, let me do something like this. I can use a default, because if S is not empty, right, at least the result will be 1. The result is at least 1, right? So let's say length atom for atom in result. So we use a default that is 1. So this is our code or format 1. Let's do a test. Solution. So here solution takes 1 but 2 given here. Let's see. We don't need to pass into this one, right? So yeah, it passes the first one. Now let's directly submit that. It passes all the cases. So now let me make some comment. So this version is very verbose in the sense that it's based on the thought that if we can find all the valid splits, then we just need to compare the length, then find the largest one. That's it. So we can easily modify this one, right? So what we can do is I'm going to change this one to be version v1, right? So for this, we don't need all the result. So here, let's maybe set it to be 1, right? Then because this is the integer is immutable, so we want to modify that. We can use a non-local keywords. So here, once we get a valid one, so I'm going to comment out this one rather than append to this list originally. So what we are going to do is we'll update the result variable, the length of the current split, right? Then the remaining part for this one is not going to be changed. So then we still have this one, but here what we want to return is just the result itself, right? So let's do a quick test. It passes example 1. Now let's look at the generic case. Yeah, it passes all the cases. It looks like faster, right? So because we save a lot of space. This is the second format. Now let me make a small tweak and also start with a new version so that you can later focus on each version. So I'm going to call this one version v2. So here, some people may do not know or may prefer not use this non-local keywords. We can also treat that. For example, we can make a list and originally it's 1 because the list is mutable. So now we can do something like this. We don't need this non-local keywords. Rather, here, what we are going to do is we want to reset result 0 as to be the original state and this one, right? Then what we are going to return is nothing but result 0. So this way, we actually modify a single element of this list, but it plays the same role as here you are using the non-local keywords. This actually touches some variable scope and the way Python pass a variable to its argument in the function. So now let's do a test again. Oh, did we test that? Yeah, let's see. Yeah, this is the second version. So I want to, this is the third version essentially, but it's the second version because it's essentially the same. So I'm going to copy this again. And I want to show you that how you can pass this current split, this is the mutable object, into the backtracking function, right? So here I'm going to use this result. I'm going to use this as 1, right? So I'm going to delete this part. And then I want to have a current split. So I'm going to set it to be a keyword argument, right? If I do not specify at the very beginning, it will be a empty set. Then what's the bounding condition? So that still I need to because this is a it's immutable. So I'm going to non-local this result. And then the bounding condition. So here I'm going to do this, right? Still max and length of the current split, and then we're going to return. And here, because we write in the current format, so actually we don't need all those, right? So what we are going to do is actually do DFS. So you can still think like the previous logic. We're going to have this words, right? So then what we are going to do is we're going to start from I+1. In other words, we want to try word s from the starting index ending at I. So we write I plus 1 here, right? So next index will be I plus 1, right? So here, because it ends at I, right? So the word we are going to consider is nothing but current. So this is the current split. So actually it equals the pre-state current split. Then union with this word, right? This word is s idx I plus 1. So this is the single element set, right? So but now it's just one line, right? So then when you do DFS, because here I'm using a keyword argument, you can just write DFS 0. And what you want to return is nothing but result. So now let's do a test. Let's see. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So I guess up to now, so we finished the coding part of this problem. So here essentially we are giving two different formats, but the same solution. So personally I feel that this different tweaks and tunes can be essential, because if you want to really understand something, so you need to understand every single details and know how to manipulate those, right? So with that said, I guess that's about it for the current problem and the current video. If you find this video helpful, you can follow up our channel to watch other videos. Thank you.